Hello, everybody, and welcome to our first set of notes for this chapter on temperature and heat. We'll be talking about a lot of different things this chapter for thermodynamics, heat exchange, all that good stuff. And today is just kind of our first dipping of the toes in talking about some of those topics. So today we're going to be focusing specifically just on temperature and heat. I'll talk a little bit about heat exchange and how thermal energy is exchanged from one object to another or from one heat source to another. But really, it's just kind of the base level stuff that'll set up what we're going to be doing moving forward. So, temperature depends on the movement of the particles. So, all matter we know is made up of atoms that are moving. Even things that are solid still have those atoms that have movement to them. In a solid, it's just that those atoms are vibrating. So, that motion of the atoms gives that object energy. So all objects have energy. Doesn't matter if they're solid, liquid, gas, plasma, they all have energy. And that's really what the kinetic theory of matter is dealing with. So it says that all particles that have matter are constantly in motion. And like I had said previously, a solid, that's vibrating atoms. So because they have that set structure, they don't flow freely over each other, but they still do have movement in that vibration. A liquid is flowing atoms, so they're flowing over around each other. They can kind of interact with each other and bump into each other. A gas, they're completely moving freely. Those particles have a lot higher energy than solid and liquid. And then a plasma, which we don't see a lot of, but then again is freely moving atoms, but they have an incredibly fast speed, the velocity that they're moving at, which is why we now have that kind of break between what we would originally just called solid, liquid, and gas. We now have that fourth phase that they've realized because there's so much more energy with that. We have really a fourth phase of matter with plasma. So temperature, it's the measure of the average kinetic energy of the particles. So we take a look for the average particle in that substance, in that sample, whatever it is that we're measuring, whatever its average kinetic energy is, so how fast it's moving, how much kinetic energy it has. That's just how we measure temperature. And we've got a bunch of different units for it. But here, the atom's mass and the speed is a determining factor for the temperature. So we have to factor in how big the object is, how fast the particles are moving. That's all part of temperature. And like I said, we have a couple different ways to measure it, which we've talked about. Last chapter when we did the gas laws, we did all three of the different ways of measuring temperature in degrees. We've got Celsius, Fahrenheit, and Kelvin. Fahrenheit, water freezes at 32 degrees and boils at 212. Celsius is a little easier. That's kind of our standard unit that we use most of the time, kind of interchangeably with Kelvin. But water there freezes at 0 degrees and boils at 100. And just remember, if we're going to convert back and forth between Celsius and Kelvin, you're just going to subtract that 273 to get from one to the other, because Kelvin is set up so that we don't have any negative numbers. So all we're doing, it's just a straight linear adjustment, where all we're doing is just subtracting off that amount to set the lowest possible temperature, 0 Kelvin, which last chapter again we talked about, that's 0 particle movement. That's 0 degrees Kelvin. It's just our conversion back and forth between those two things. So, jumping back ahead. So our way of measuring those, we know a thermometer is how we measure the temperature of something, and that's based on the idea that the liquid that's inside, again, a kind of an old school, what we would call an old school mercury, they don't use actual mercury anymore, but mercury thermometer is all on how much that liquid inside it expands or contracts based on the temperature that it's around. So the liquid inside expands at a certain rate, and that tells us, based on how far it's expanding, what the actual temperature that it's experiencing. And this is all based on the idea of thermal expansion, where if something has a higher energy or a higher temperature, it's going to expand and take up more volume. So all gases and liquids do. Most solids expand when their temperature increases. This is why we have bridges, structures that have kind of these little gaps, or you can see here this little joint here that allows that thermal expansion and contraction to happen so that you're not going to have buckling and any kind of damage happening to your structure when that happens. So in the summer and they expand, these gaps will fill in and be tighter. When it's colder out, they're going to contract because that, again, that mass, that solid is going to take up less physical volume by a very, very small amount, but this joint kind of just allows for that motion, that expansion and contraction, that expansion and contracting to happen without any gaps that are going to be dangerous or they're not going to have any damage caused to the structure. So with energy, we know that we always are trying, just like with temperature that we talked about with the gas laws, it's always trying to find an equilibrium. So heat is just the flow of energy from a higher temperature to a lower temperature, or a higher energy to a lower energy. They're always trying to work to try and find that equilibrium. And just that transfer, that flow of energy from one to the other is what we call heat. The thermal energy is the total amount of kinetic energy that the particles in the object have. So heat is that flowing of energy. Thermal energy is just that total amount that our object or our sample has. And like I had said, it's going to try, ahead of myself. I have a slide ahead. When we measure heat, we've got the two different units that we talked about yesterday. We've got the calorie, which is the amount of energy required to raise 1 gram of water by 1 degree Celsius. That's just the definition. That's kind of the standard way that we define a calorie. And our joules, not J-U-U-L, I know you're going to make that joke, joule, is equivalent to, again, the energy required or the amount of work done to move an object 1 meter with 1 newton of force, which is, again, going way back to beginning of first semester when we talked about energy the first time around. So this is the conversion back and forth between calories and joules. So 1 calorie is 4.18 joules. So eventually when we start getting some actual math-based problems, that's going to be the conversion back and forth. As with electricity that we'll deal with in a chapter or two ahead of now, some substances are more willing to accept or exchange that heat. Some are more resistant to a temperature change and accepting or a giving away of their heat, their thermal energy that they have. And specific heat is the way that we kind of can measure how likely or how willing that object or that substance is to either accept that thermal change or give away that thermal energy. So the specific heat is specifically the amount of energy required to raise the temperature of that substance, 1 gram of that substance, by 1 degree Celsius. So just kind of our set scale, water is a 1.0 in its specific heat. So since, again, a calorie, that is the amount of energy required to raise that 1 gram of water by 1 degree Celsius, its specific heat is 1. So then everything else is either higher or lower than that, depending on how easily that temperature is changed. So something with a lower specific heat is more willing to either give away or accept that thermal energy. Something with a high specific heat is more resistant to changing its temperature. So it's either going to retain that temperature, that thermal energy it already has, or it's going to give away that thermal energy, less likely. So transferring heat between the 3 different things, again, we talked about this yesterday, the 3 different ways that heat can be exchanged, that heat can happen, right? That movement of energy is through conduction, convection, or radiation. So conduction, again, that has to have a physical contact of particles in order to exchange that energy. So like I had alluded to kind of on the last slide with specific heat, things that transfer their energy easily, either giving it away or accepting it, are what we call conductors. Insulators are not as accepting or readily able to change that thermal energy. So something with a very low specific heat is going to be a great insulator because it's less likely to give away that thermal energy. A conductor has a very high specific heat, or sorry, I had that the other way around. A conductor has a high specific heat. I'm sorry. I'm going back and forth on this. I'm recording at 11 o'clock at night. Insulators, because it takes more thermal energy to raise that temperature, are going to have a high specific heat. Conductors, since they easily change that thermal energy, have a very low specific heat. So low specific heat are conductors because, again, they're willing to change that thermal energy. It's going to require less energy to change the temperature of that substance. An insulator, which resists that temperature change, is going to have a high specific heat. So just an example here, a cup of coffee, a cup of cocoa transfers heat directly from your hand, from the cup to the hands. If you're cooking an egg, they have that conduction would happen from, the pan gets heated up, and then that pan conducts that thermal energy directly to the egg or whatever it is that you're cooking. Convection, again, we talked about this today. Convection is when we have that flow of a fluid. So this is could be with a gas or with a liquid, but we have this exchange, kind of this flowing of a large number of particles in the same direction. So we're taking and specifically going through and kind of going from something that has a high temperature, so a warmer part of the liquid, a warmer air, we know that rises because it's less dense than something that's colder, and then that is then replaced by the cold water or the cold air that it's kind of pushing down on. So when you're boiling a pot of water, again, that water that's closest to the pan, that's closest to the flame, gets warmer and gets pushed up to the top, and then that cold air flows down because it's more dense, and then that's still going to be heated up then. So then that flow of water, that cycling from hot to cold, allows it to be heated more quickly. And the same thing happens with your heater. Now this is an old example of this because most houses, maybe yours does, have an actual radiator, and they're placed very specifically in the room that allows for that flow of air to happen. They're going to put it in a spot where when the heat rises, it's circulated through the room, so the cold air gets pushed back down and heated back up, and there's that flow that happens with convection. This actually happens in nature too. The atmosphere actually has convection that happens, and again, it's because the ground is warmed up by the sun, so we have all that salt, that radiation that's being absorbed, kind of the next thing we're talking about with radiation. So the ground is warmer, so that's going to heat up the air that's close to it, and then that hot air rises, pushes that cold air back down, or depending on, again, which part of the cycle you're thinking of, the cold air falls because it's more dense, and then again that's heated up, and we just kind of have that cycle happening. This is another thing, along with our different pressure systems, that kind of causes that weather that we talked about last chapter, again, with atmospheric pressure. So our last one is radiation. Like I alluded to, this is, the sun is our best example of radiation as a source of heat energy. This is the one that happens anytime you don't have a physical contact, you don't have particles that are actually bumping into each other or flowing at all. This is going to be that invisible way of increasing the temperature. So this happens when you have any kind of electromagnetic wave, so visible light, microwaves, infrared. That's where that energy is coming from. So that electromagnetic wave is going and interacting with those particles. So the radiation strikes the atoms in your body or in the substance that we're dealing with, and that's where that energy comes from. So this slide is great if you can just remember this one, if you just write this one down, take this one in your notes. This is just the best summary that we have for the 3 different ways that thermal energy is exchanged. So again, we talked about conduction as the transfer through direct contact. Energy flows from always the warmer object to the cooler one, the higher energy to the lower energy, and this continues until they normalize. So if you have 2 objects that are interacting with each other, they're going to keep doing that until they reach the same temperature. Convection, again, is that gas or that liquid, that flowing of movement of particles, so that we have that circulation happening. And again, radiation, that's that invisible exchange of energy. So for your homework tonight, it is a quiz. I already have it posted. It's already open. It's due next Tuesday, since you guys have the next 5 days off Lucky you. It is 24 questions, just like with most things. You got unlimited attempts. If you have questions or struggles while you're working on it, let me know. Otherwise, thanks for watching, and I'll see you guys as soon as you're done watching this video.